I1 squared plus I2 squared plus I3 squared, that is the Casimir operator which commutes with I1, I2, I3. And so this can be taken, and one of the components can be taken, and that is generally taken as component 3. That is the way isospin is. So a total isospin and the third component is conserved. If you go to SU3, similarly there are actually there are two Casimir operators for SU3, and that and how many commuting generators are there? Two of them I already mentioned, that for in 3×3 traceless Hermitian matrices there are two. One we called it I3 or lambda 3/2 in the Gelman's notation, and another was I8. So this remember in the actual physical application was the third component of isospin and hypercharge. So third component of isospin and hypercharge are conserved. Similarly, when you go to higher and higher dimensional SUNs, there will be there will be that many number of conserved charges, not the total number of generators n squared minus 1, but only the commuting generators plus something which corresponds to Casimir operator. And in SU3 there are actually two Casimir operators, but we don't really calculate those Casimir operators. Actually they are some of the squares of all the generators plus some of the cubes, I think. Instead of that, we simply say the representation. If in a reaction the left hand side total is an octet in SU3, the right hand side also has to be octet. So that takes care of the Casimir operator conservation. Okay, Casimir operators and the diagonal generators, those are the conserved quantum numbers for non-abelian theories, and those are the generalizations of the Noether's theorem. Okay.
The G that you have written in the Yang-Mills Lagrangian.
Yeah.
So what is that physically? Physically, it looks like a charge. A QED Lagrangian.
In the QED Lagrangian, yeah. This G mu nu is is the analog of the F mu nu. F mu nu, remember, had only this term d mu a nu minus d nu a mu, because a mu and a nu commute there, they are numbers. So this is a more general form of the, you can call it field tensor if you like, because in the free field case, when they are not interacting with other particles, only that determines the dynamics. So in the dynamics, it is a free field tensor which comes, which are basically derivatives plus a quadratic term. I mean, what is the connection between electric and magnetic field and the vector potential a mu? It's the same.
So now I'm asking about that small g.
Small g.
G.
Oh, small g. Small g is the coupling constant. Coupling constant of the Yang-Mills field with the Dirac field psi. In the case of QED, that coupling constant is what we have been calling electric charge. But in Yang-Mills field, so for every group, there will be one coupling constant. Ultimately, when we construct the standard model, you will see that G becomes a coupling constant for the weak interaction, and for QCD, G becomes a coupling constant of the strong interaction. So there will be so many coupling constants in the theory. Since the standard model is based on three groups, SU3 cross SU2 cross U1, we will move towards that. You will have three coupling constants in the standard model. One you can say is strong coupling constant, two for the electroweak interaction. Okay. So now I want to prove this transformation for this field tensor G mu nu. So let us do that. Before that, I could have pointed out one more thing which is very important. Remember, G mu nu is quadratic in W. So since G squared comes here, capital G squared comes here, there is in addition to the quadratic term, which is in some sense the kinetic energy of the gauge bosons, there will be two kinds of interactions. One cubic in W and another quartic in W. So this leads to, in pictorial language, where each wavy line represents a W mu, okay, plus a quartic term. So the typical non-abelian vertices cubic and quartic are contained in this term, because of this disk. Because it is a linear term and a quadratic term. Yeah. So square of that will contain a cubic term and a quartic term. Okay. So remember in the definition of W mu also G will come, and so actually this will be proportion. This coupling will be proportional to G, and this will be G square. I mean, those are details which we will see later. But it's better to recognize this straight away. So let us now try to prove this. As I said, there is no physics there, it is only algebra. You have to keep track of indices properly. So maybe most of these I will remove, keeping only some of them. This is an important equation. So when W's transform like this, how does G transform? That is the question we are asking. So I will keep this equation. So using this equation in the definition of G mu given there, you can see that G mu prime is equal to G mu prime by definition is d mu W nu prime minus d nu W mu plus the commutator term. By definition, this is the transformed field tensor. And for that you substitute from here, so there will be so many terms, d mu whenever I write like this, it means this derivative operates only on this, does not go any further. Otherwise I have to put an additional bracket minus remember G mu nu as defined here is antisymmetric. This is already antisymmetric, and the commutator is antisymmetric. So you can see that G mu nu is equal to minus G mu, antisymmetric in the two indices. It is an antisymmetric field tensor, exactly like electromagnetic field tensor mu nu. So I will write this and then simply write like this instead of repeating all those. Mu goes to nu goes to mu, the interchange term, but with a minus sign. So I have done this. Now I have to write this, the quadratic term. Again, mu going to nu terms. Okay, I think that's all I have got. But now I have to expand and write all of them. So this since derivatives are there, some more terms will come, and then you have to multiply these terms. So many terms are going to come. I am just differentiating, that's all. I think if there are 3 factors, there will be 3 terms. I have written the 3 terms. Similarly, here I think only 2 terms will come, right? I think that's all. No, I dealt with only the first line. Second line has yet to be done. Second line is minus I. Well, just 4 terms will be there, so let me write down all the 4 terms first. I hope you know how I got this. When I multiply this by this U inverse and U can be removed, since U inverse U1. So that is why W mu comes. So similar things I have to continue to do. U, this is d mu U into U inverse. So that cannot be removed because this is d mu U into U inverse. D nu, this is again d nu U into U inverse minus U W mu U inverse U inverse Actually, you can do it at home, at leisure, without making any mistakes. This, I don't know why I wrote this, there is no curly bracket. I think that's all, I have got everything. Now, straight away, this thing can be omitted, because there is a d nu term, and then there will be minus d mu, but they are the same. And that will be negative of this because of this minus sign, and so they cancel. So I can straight away remove this because of the antisymmetry in mu nu. Okay, let us now go to the next page. I wish I could have kept some of this. Yeah, I said there will be a coupling constant G here on G squared, and that can be seen because of this G. So this into this will give the cubic term, and this into itself, so G squared. So this is G squared, and this is G. So these are the 2 basic equations. Let us keep. And we transform this, and we have written down the G mu nu prime. So I have to deal with this now. So this I will remove. So this whole thing. D mu U. Oh, some simplification can be done here. d nu u into u inverse can be written as minus u into d nu u inverse. That is because of this kind of thing. Since u inverse by definition of inverse is 1, I can differentiate this and get d mu u into u inverse plus u into d mu u inverse is 0. So d mu u into u inverse is the same as minus of u into d mu u. Similar things can be done with putting u on this side. So I will rewrite this d nu u into u inverse as u into d nu u inverse. If we write like that, then this u can be cancelled with this u inverse. Similarly, I think the other term also. I think this also can be written as minus u d nu u inverse. Then this u and u inverse will cancel, so that also can be simplified. So the first term is d mu u w nu u inverse plus I d mu w nu. I think there is a u here. I'm sorry, the whole thing is wrong. I am just rewriting those things, that's all. U d mu w nu u inverse plus u w nu d mu u inverse minus I d nu u d mu u inverse plus the anti-symmetrization. So I have dealt with the, I think this first line. Yeah, now the second line. After taking care of these two identities which I made, so it becomes minus I u w mu w nu u inverse minus I d mu u d mu u inverse plus u w mu d nu u inverse minus d mu u w nu u inverse and anti-symmetrization. That's all. Now there are many cancellations. So let me write down, instead of writing that mu nu, that notation, anti-symmetrization, let me just write it fully. Then only cancellations can be seen. First line I am just repeating. Then mu nu interchange. So I should write here mine with a minus sign d nu u w mu u inverse minus sign u d nu w mu u inverse, again minus sign, this is plus u w mu d nu u inverse minus I d mu u d nu u inverse. So that is this is the first line completely anti-symmetrized, written explicitly. Similarly, second term, all the signs have to be changed, so it will become plus I W nu u inverse minus I d nu u inverse plus u W nu u W nu u inverse minus anti-symmetrization minus I u W nu u inverse plus I d nu u inverse plus u W nu d nu u inverse minus d nu u inverse. That's all. We have written all of them. There are 4 lines. And what are the things which cancel? You see, this cancels neatly with this term. And this I will use this notation by the angle at which I cross out. This cancels with this, right? Yeah, this. And this I will use this notation. This cancels with this. This should have been plus, that is why I made a mistake there. Then this cancels with, again I made a mistake, this should have been plus, and this cancels with this. I think we have done all the cancellations. So let us recover what is left. You can see what is left can be written as u d mu W nu minus d nu W nu u inverse minus I commutator of W mu W nu into u inverse. So that is what we wanted to prove. Therefore, and this is nothing but u, I forgot to write here. We started with g mu nu prime. So g mu nu prime is equal to u g mu nu u inverse. That's all. And hence, in the Lagrangian, the trace comes, and so it is invariant, where u and u inverse will cancel each other, and so the Lagrangian what came? Trace of g mu nu came, and that will go into you proved that this is equal to trace of u g mu nu u inverse u g mu nu u inverse. These u inverse u will eat each other, that will go away. And in trace, you regard this A and this regard A into B is the same as B into A. So this u inverse will eat, can be put here. So this is the same. So therefore, E is invariant. So we constructed an invariant Yang-Mills Lagrangian. Okay. Any question? These are pure algebra. Please verify it for yourself. If there are any questions, I will take it up. Otherwise, I will rub it off and go to lecture 12. So you can say gauge theory continued. Okay. So what we have done is non-abelian gauge theory. Now something more has to be done. The most important thing is spontaneous breakdown of symmetry and Higgs mechanism. So I am going to develop the notions connected with that now. Development of non-abelian gauge theory with spontaneous breakdown of symmetry. So I am taking most of it from my lectures, which I mentioned earlier, building up the standard model of high energy physics. Unfortunately, this is not in archive. It is in some old lecture notes, lectures by GR. But Satya has got a copy. I hope you can get it from him. Okay, Satya?
I have sent it already.
Satya says he has already sent it to you all. So please look at that. Okay. The first thing I proceed step by step. First thing I do is go back to the U1 gauge theory. Of a scalar field. So far I had written psi as a Dirac field, but now let us consider now scalar field is going to play an important role. So the Lagrangian for a scalar field is, let us take it as a complex scalar field. If it is a real scalar field, it will describe scalar field, the mu is a vector field, that is why it describes photons of spin 1. And psi is a spinor field, so it describes spin half particle like electron. Scalar field is a single component, so it will describe a spin 0 particle. Spin 0 particle is going to be introduced here. We already had pion and kaon, which are spin 0, but they are not elementary, they are composite. The real elementary particle is what we are going to introduce, and this will play a role in Higgs mechanism, and it will manifest itself as a spin 0 particle, which was finally discovered in 2012. Okay. So this is the quantum field theory of that. Actually, we don't use quantum field theory as such. Classical field theory is enough. You can consider it as a classical field. The quantum aspects rarely plays a role here at this stage. But when you consider the particle nature, then it's the quantum nature of the field only will give you quanta. So it's a complex field, so the particle and antiparticle are different, like a charged particle, for instance. So it's a complex field, so I will call it phi star here. Strictly speaking, in the quantum version it should be replaced by Hermitian conjugate, but since we are using only classical, phi is the field, its complex conjugate, so take the derivative and multiply together, that is the so-called kinetic term, and then there will be a potential term, which is a function of only phi star phi. And phi star phi for us will be taken as one quadratic term with a constant, which will play the role of the mass of the particle, and then there will be a quartic term which will play the role of interaction. The interaction can be denoted by this diagram, phi star, and the coupling constant is this is called the lambda phi power 4 coupling, and this is the mass term. So the Euler-Lagrange equation again, that is dl by d phi is equal to d by dx mu of dl by the derivative of phi. Euler Lagrange equation will give you. Please verify this. The box plus mu squared phi equal to minus 2 lambda phi star. It's a quartic term, but in the equation of motion, since we have differentiated with respect to one field, it will come as a cubic term. This is nothing but d squared by dx mu into dx mu. 4-dimensional Laplacian, written in terms of space and time separately, it will be d squared by dt squared minus Laplacians. So this is the wave operator. So this is the wave equation for the scalar field phi. So this Lagrangian also is invariant. Under first the constant phase transformation, phi goes to e power I alpha minus phi alpha constant. So by Noether's theorem, there will be a current which is microscopically conserved, namely, and that current you can work out. There are prescriptions for doing that. I don't want to go through all that. J mu will be phi star d mu phi minus d mu phi star into phi, and this current will be conserved. So again from this you can get d by dt of J0 d cubed x by bringing out the divergence and integrating it over all of space using Gauss theorem and taking the surface term to be 0. So now we enlarge the symmetry to space-time dependent phase transformation alpha constant to alpha x, and L is not invariant now unless we do some modifications. Because phi goes to e power minus I alpha x. This is a repetition of what we did for psi. And d mu phi, since d mu phi comes here, it comes here also. The Lagrangian is not invariant. D mu phi will go into e power minus I alpha d mu phi minus I d mu alpha into e power minus I alpha phi. So introduce a mu and demand that a mu goes to a derivative term. I mean, you have to add a derivative term 1 over e d mu alpha. Then the covariant derivative d mu plus I e a mu. If phi goes under this and d mu goes under this and a mu goes under this, then if you take this combination, the derivative term cancels, so only the simple phase factor comes. Whereas for phi star, same thing but with a minus sign. So if we replace those d mu phi and d mu phi star by these covariant derivatives, if d mu operates on phi, you have to add this, If d mu operates on phi star, you have to do this, both of them come. So you multiply them together and then also add the dynamical term. For once you introduce the field A mu, the dynamics of A mu will be described by this term. Where F mu nu is same as before, d mu A nu minus d mu A nu. In that case, the Lagrangian will be invariant. This we already know in the case of psi. We called it psi at that time, now it is phi, but the principle is the same. By the way, this is called the Klein-Gordon equation. If you put psi equal to 0, del plus mu squared phi equal to 0 is called the Klein-Gordon equation. Klein-Gordon equation, which came before Dirac equation. In fact, it came even before Schrodinger equation. Schrodinger straight away wanted to write down a relativistic wave equation for electron, and he wrote this and then put the Coulomb field here and then calculated the energy levels. It did not agree with Bohr theory at all. So he threw it out and took the non-relativistic approximation of this, which is what we call Schrodinger equation now. So it's really Schrodinger equation. And then of course the rest of the story you know. And this Klein-Gordon equation itself had some other problem which was rectified by Dirac, because the Klein-Gordon equation has got second order derivatives here, which leads to some problem, because it did not have the interpretation of the probability amplitude, unlike Schrodinger equation which had first derivative, which can be interpreted as a probability, conserved probability interpretation, because that is very important. Interpretation came from Born, Max Born. Only after the Schrodinger equation itself had full meaning, because there was a probability conservation. But such an interpretation could not be given for Klein-Gordon equation, so it was given up again. And then so the Dirac's principle was all elementary basic equations should have only first derivative in time. That was one of his principles, and he managed to do it, and that was Dirac equation. Remember, in Dirac equation, I gamma mu d mu only first derivative comes, and in that process only gamma mu he invented, and that led to antiparticles and so on. Then after that, once antiparticles were discovered in the case of, I am giving a brief summary of relativistic quantum mechanics, which is necessary before you go to quantum field theory. So after that, people realized that for relativity there has to be antiparticle, and hence they interpreted phi not as a wave function, which fails, because if it is a wave function, probability amplitude has to exist. They reinterpreted phi as a field, classical field, and quantized it and got particle and antiparticle here also. That was done by Pauli and Weisskopf. Pauli and Weisskopf recovered the abandoned Klein-Gordon equation and gave new life to it. Now we know Klein-Gordon equation also is as decent as the Dirac equation, but phi has to be interpreted as a quantized field. And in the Dirac thing also it became quantized field, but that is another story. So I just sort of summarized the relativistic quantum mechanics for you. Okay, so let us come back to this. Covariant derivative acting on phi star phi and then the potential term. Is invariant. Invariant under the, let me introduce the terminology which I mentioned, general U1 transformation, namely space time dependent U1 transformation. That is the scalar field interacting with a U1 field. I will not call it electromagnetic field. This will be another kind of U1 field which will come in standard model, but basically it is like electromagnetic field. So let us go further in this canonical Lagrangian framework. Once Lagrangian is given, you can go to Hamiltonian also. So let me do that. To go to Hamiltonian, the route is this. You have to define the canonical momentum. If a coordinate is phi, see phi at every point in space time is a coordinate. I mean, that is how it is a field theory. Infinite number of variables instead of finite number of variables like in particle mechanics. In field mechanics, there are infinite number of variables. Field at every point is an independent variable. So differentiate this with respect to the velocity of that variable, namely phi dot. So phi dot means anything dotted means time derivative. You can at once see that in contrast to Lagrangian, the Hamiltonian formalism will not be covariant. Lagrangian is a Lorentz invariant quantity. There are no index here, and everything, all the indices are contracted there. So Lorentz covariance is manifestly maintained. But Hamiltonian formalism, time is picked out separately. And so Hamiltonian formalism is not manifestly covariant, but it can be made relativistically okay. That has to be verified separately. Here it does not have to be verified. Once you write down in the covariant notation, automatically it is invariant under Lorentz transformation. In every frame of reference moving with respect to each other with constant velocity, the the physics will be the same. I mean, that is the main principle of relativity. It's automatically there as soon as you write down the equations in a covariant form. That is the reason for covariant formulation. But Hamiltonian formulation cannot be written in a covariant way. So that is pi. And here again, phi and phi star are considered as independent fields. So we have to define phi star, the canonical momentum corresponding to phi star as the derivative of that. And Hamiltonian is defined as Hamiltonian density we are talking about, just as we had Lagrangian density. To get the total energy, you integrate it with respect to d cubed x. That is the total energy. Pi into the corresponding velocity, similarly for the other one, phi star, phi dot star, minus the Lagrangian. That is the general definition of Hamiltonian. Hamiltonian is minus the Lagrangian plus the momenta times the corresponding velocities. That is the general definition of the given Lagrangian. You can always go to the Hamiltonian using this. Now substitute for these things. Namely, I am going to substitute Lagrangian, that Lagrangian, I think. No, we are, I am just considering the Lagrangian for free field only, which I rubbed off here. Remove these things, remove this mu nu term. So only the derivative term and the potential term. But remember this d mu is d0 d0, I mean d0 phi star into d0 phi, that is phi dot star into phi dot minus the spatial thing. So I am going to separate the time and spatial because for forming the Hamiltonian, that is what we have to do. And the time parts are simply phi dot star into phi dot, and the spatial parts are simply gradient of phi star dotted with gradient of phi. Then minus, let me write down the explicit form of V, mu squared phi star phi minus lambda phi star phi. So this is actually free scalar field. I am writing down the Hamiltonian density. So I am now coming back to the original free scalar field, not this enlarged system. Scalar field interacting with a vector potential, just the original Lagrangian which I rubbed off, which was here at the bottom. And for that Lagrangian density, this is the Hamiltonian density. This can be simplified. And another thing, important thing to note is Hamiltonian has to be written in terms of momenta and the coordinates, field variables, and the corresponding canonical momenta. No time derivative should occur, whereas Lagrangian involves variables and the time derivatives. So all the time derivatives have to be expressed in terms of the momenta, but that is very simple, because dl by d phi dot, if you look at it, you will find it is simply phi dot star, and this is nothing but phi dot, just from this term d0 phi star into d0 phi. So differentiating it, you get that. So momenta are nothing but velocities. In a simple mechanical problem also that is true, momenta are nothing but velocities apart from a constant which we call mass. So this can be written as pi pi star, this also same, pi pi star, and this also same, pi pi star. So one pi pi star will cancel. So the result is pi star into pi plus gradient of pi star, gradient of pi. I think I made a mistake. It should have been plus, right? The minus v is there, and there is another minus, so it becomes plus. Plus v squared h star pi plus lambda h star pi whole squared. Note that this is explicitly, manifestly positive definite. Maybe 0 if everything is 0, but it is a vacuum system. Otherwise, it is positive, as it should be. This is what is called the potential, and this is actually the kinetic energy, strictly speaking. But usually, so strictly speaking, all these should be considered as potential. But we use the notation this is v, because here the derivative with respect to space are involved. Okay. So the Hamiltonian energy density itself is positive, so energy is positive as it should be. So it is a decent theory. Now let us try to interpret the various terms here. There are two.
There is some problem that every 10 seconds the screen is going black.
Pardon me? Every
10-15 seconds the screen is becoming blank.
Oh. There is some problem. Please check. Yeah, like this, right? There is some loose connection or something.
I hope others are also seeing it.
Yeah, I am also seeing it.
Yes, sir. Same problem, sir. Here also.
Yeah.
but anyway it is coming back, so just for 1 second it disappears. So let me continue. He will set it right, I am sure. So this is the energy density, which can be roughly written as kinetic energy of the field and the potential energy. You can see that lambda has to be positive. It is very important, because if lambda is negative, for large field configurations, this term can take over. This will be larger than this, whatever may be mu squared, this will become larger than this. Then the energy density, I mean, this can compensate for all these and become negative. And by taking phi sufficiently large, and phi star phi whole squared will be positive and lambda is negative. So the energy density will go down and down negative. It will be an unstable system. We can never allow that. Energy density can never be unbounded from below, then you can never have the proper dynamics. For proper dynamical system, energy density has to be bounded from below, and that will happen only if lambda is positive. So this coupling constant lambda of lambda phi power 4 theory has to be positive definite. On the other hand, there is no such requirement for mu squared. Note that there is no such requirement for mu squared. So mu squared can be positive or negative. This is an important point. Although this may be negative term, but this will overwhelm mu squared, so there is no unboundedness here. If phi is very large, this will take over. So mu squared can be positive as well as negative. So we should consider theories where mu squared can be negative as well as positive. For mu squared positive, the potential we plot as a function of phi. I am considering a single component phi rather than phi and phi star here. Single component phi, it is just a parabola, quadratic. V like this. So this is the case mu squared positive. And this is the case when mu squared corresponds to the mass of the the plane cordon particle, the spin zero particle, and there is nothing more to be said. There is nothing more of interest here. But the case which we are going to consider is mu squared negative. When mu squared is negative, the form of the potential, let me start from here. When mu squared is negative, so for small phi, it will be negative like this. But then soon the lambda phi star phi term will take over, and so it will become like this. V as a function of phi, consider phi as a real thing in order to picture this properly, then it has this behavior. So this is the case mu squared negative. This is what leads to spontaneous breakdown of symmetry, and this is called Goldstone. It was Goldstone who first pointed out this possibility. So let me call it the Goldstone model. So let us discuss this in detail. For that, let me go back to the case where phi is complex. Then phi is not a single axis. Let us introduce phi. Let me write down phi star as phi 1 and phi 2. I mean phi as phi 1 plus I phi 2. We can rewrite the Lagrangian in terms of phi 1 and phi 2. So in terms of phi 1 and phi 2, B will look like this. this diagram will be replaced by a three-dimensional diagram now. This is again potential. Let me indicate the three dimensions by drawing a circle here, and similarly here also please draw a circle. So, instead of the minimum having only 2 points, here the minimum occurs all over a circle. That is the important point you should remember. This is the minimum of the potential and the maximum is here. Here, in this case, we normally say that the minimum of the potential, that is the point at which the field is 0, and then we quantize the oscillations around this and get the particle, the quanta. That is how the quanta arrives. But in this case, that point, that symmetrical point, cannot be chosen as the as the ground state of the system. Here it is the ground state of, this is the ground state of the system. Here corresponding point is this, which is not the ground state, because it is an unstable equilibrium. Here it is a stable equilibrium. This point is a stable equilibrium. Here this is a maximum of the potential. It is like standing at the top of a mountain, and any small wind disturbance will take the ball which was there down below. So, so we cannot take this as the ground state, and we have to choose the ground state as any point along the circle. Remember, we are talking about this theory which is a U1 symmetry, and the U1 symmetry is just a circular symmetry. U1 is just a circular symmetry, because that changes the phase of phi. When you change the phase of phi, it is equal, that alpha is simply this angle, any angle. So, so there is a circular symmetry in this problem, it is clear. The original Lagrangian, and the Lagrangian we have forgotten. Lagrangian is simply this. I am sorry, d mu phi star d mu phi minus v. So, this has the U1 symmetry which corresponds to a circular symmetry. That is the point I want you to mention. There is you can imagine geometrically that there is a circular symmetry. But if the ground state is taken here, of course, the whole system will have circular symmetry, but that cannot be done, because that cannot be the ground state, because it is an unstable equilibrium. We have to choose one of the points along the circle as the ground state. That is the important point. But once you have chosen any one of these points as the ground state, the circular symmetry is broken. So, that is the spontaneous breakdown of symmetry. A point along the circle is chosen as the ground state. As the ground state of the field system, symmetry, the U1 symmetry is broken, the circular symmetry is broken. So, that is spontaneous. So, this is SSB. So, that is all spontaneous symmetry breaking is. So, let me, I have said so many things, I am going to put all those things in the form of equations now. So, let us write down V as, I am going to rewrite lambda. See here, I think I made a mistake here too. Remember, 0 of this was here, so I should have drawn the circle below. I don't know how to do it now. Remember, this part was negative and that part is negative. Now I am going to lift it. I am going to add a constant term to B, and so that this minimum comes on the 5152 plane itself. So that is easily done. You have to simply choose a constant. If you choose a constant properly, the whole thing can be written as this way, where what is phi 0? Phi 0 is basically the radius of the circle. So I have added a term 2 lambda phi 0 squared into phi star phi. I am sorry, phi 0 power 4. Yeah, basically lambda phi 0 power 4 I have added or subtracted. I am square of this. The original potential is simply this, apart from a constant addition or subtraction, whatever you can check. So instead of using lambda, you can use this phi 0. There are only two constants, mu squared and lambda. So phi 0 can be given in terms of this. So the radius of that minimum potential is given in terms of mu squared and lambda. Or phi 0 is minus mu squared over 2 lambda. Lambda is positive, mu squared is negative. So remember, phi 0 is positive. Phi 0 squared, is it? Yeah, this is phi 0 squared. It has to be positive, and it is positive because mu squared is negative. Remember, we are considering mu squared negative Goldstone model. That Goldstone model will what lead to spontaneous breakdown of symmetry. So in the field theory, if mu squared happens to be negative, there will be an automatic breakdown of symmetry. That is called spontaneous breakdown of symmetry. Now, how do we put all these things explicitly in terms of equations? For that, write down phi, that complex field, as a radius parameter and an angle parameter. Remember, phi corresponds to two real fields, phi 1 and phi 2. So I have changed the variables. Instead of Cartesian coordinates phi 1, phi 2, for the field I am going to use polar coordinates, the radius and angle like thing. Rho and theta are real. So again there are two fields. So rewrite your Lagrangian density, which again I have rubbed off, in terms of these fields. So it looks like this: d mu rho plus rho square. Please verify this simple algebra. Minus lambda. Phi star phi becomes simply rho square minus phi 0 square whole square. So that is the Lagrangian density. So we are going to choose one of these points. So now I have again shifted, so you can even draw it now below, so that this is the minimum circle which lies in the phi 1, phi 2 plane itself, and the radius being phi 0. So you can see that the minimum of this will come when this is a rho. When rho, minimum of rho is a field, remember, and the minimum of rho has to be equal to phi 0, because minimum of this will come when rho equal to phi 0. That is the minimum. So that is the ground state of the system. In field theory, that is called the vacuum expectation value of rho. So that is the notation I will use. And that has to be a constant. Remember, these are all fields that are functions of x, and I am plotting this at one point in x. But at least this phi 0 has to be the same at all points because of the homogeneity of space. So it is a constant. Phi 0 as well as rho vacuum expectation value are constants, although rho in general is not constant. In fact, I am going to redefine the field. Eta x is obtained by subtracting this rho vacuum expectation value, because then it will be a normal field with zero vacuum expectation value. In vacuum it is 0. Whereas this field rho has a funny property, in vacuum it is not 0, but it is simply taken care of by subtracting that field and redefining a field eta. Eta has the property its vacuum potential is 0. So, it is a conventional field and you can quantize it. Essentially what we are doing is we are, let us say that this is a vacuum state you have chosen, and then the oscillations around that correspond to the quanta of the eta field. We now call it eta field. It is the same as the original rho field. The radius field of the phi become this. So, what happens to the other fields? So, let us go back to this. This is very clumsy here. I don't know what to do. I should have drawn it bigger. That is the vacuum circle. Right. So, again this is wrong. No, this may be right. Only the axis is better. Take like this. So that it is obvious that the this is the minimum. We can choose the minimum anywhere here. So let me choose it here so that it can be. We have chosen the minimum here, okay? And this radius is phi 0. So now think what we have done is the transformation of the field variables, transformation of the modes. Originally there were two Cartesian modes, Cartesian like modes for the field, but now we have chosen the polar coordinates as the mode description. So there is one radius type of mode and another angle type of mode. Now you can see that the angle type of mode describes motion of the field along the circle, whereas the radius type of the field will be going perpendicular to that circle, either climbing this hill or this hill. So you can see that when the mode which corresponds to the theta, there is no energy. I mean, you don't have to expend any energy in going around that circle because the potential energy is 0. All over the circle, the potential energy is 0, especially after a shift to the potential. So there is no energy involved in moving around that, and so that corresponds to a 0 mass. By energy here we mean the relative sigma energy, which is the root of p squared c squared plus m squared c power 4. When energy is 0, so p also is 0, m also is 0. So that mode corresponds to a 0 mass mode. On that mode now we have made one more transformation, call it eta. So that is the eta. Motion along the circle, that is the eta, whereas motion perpendicular to it going either this way or this way corresponds to, no, I am sorry, it is the other way. This is eta and this is theta. Remember, there are two variables instead of rho, we have got eta, that's all. Theta still remains. So theta corresponds to a massless mode. Two modes. Instead of phi 1, phi 2, we have gone to this description, eta and theta. Theta is massless mode and eta massive. So the correct way of describing the case when mu squared negative, by the way I forgot to mention, when mu squared is negative, there were many people, some famous persons also are involved in it. They called it the tachyon, because when mass squared is negative, by following the relativistic kinematics, you can show that the particle always travels with speed higher than that of light. So they called it tachyon. You see that that is not the correct interpretation of mu squared equal to smaller than 0. It's an unstable system. It is like choosing choosing the ground state to be at the top of this potential. So it is just nonsense. So there is no such thing as tachyon. Correct way of interpreting it is, instead of the two Cartesian modes, we have to go to the polar modes and then shift the rho, and then everything is fine. Only thing is there is one massive and one massless mode. There is no tachyon. Please remember that. So there is a massless mode, that is the bad news for particle physics. This massless mode is called Goldstone boson. Of course, here we are considering only one model, but Weinberg, Goldstone, and so on, proved a theorem called Goldstone Theorem. The theorem states that any spontaneous breakdown of symmetry will always lead to a massless boson, which is called the Goldstone boson. This was proved by these three gentlemen. That is bad news for particle physics, because then we cannot apply a spontaneous breakdown of symmetry in particle physics. There is no such, both are spin zero particles. There is no such spin zero massless particle which would have been discovered long ago. If there were a spin zero massless particle, that will lead to a long range interaction like electromagnetic interaction. Nobody has seen such an interaction. So it is very easy to say that that is wrong. There is no such Goldstone boson. So this proved a stumbling block for a long time in applying spontaneous breakdown of symmetry in order to construct viable theories for particle physics. And it is Peter Higgs who proved that this Goldstone theorem is wrong. This Goldstone theorem is correct only for if the symmetry which is broken is a special symmetry. If it is a general symmetry, gauged symmetry, the Goldstone boson disappears. That is what I am going to take up next. That is Higgs mechanism, and that is what allowed people to construct the correct electroweak part of the standard model. So that is the next thing to do. So I will do it next week. Okay. If there is any question, you can ask me now. I'm sorry, I exceeded the time a little.